All right, guys, so I want to start talking about percent composition. And notice that I skipped the first two slides of the PowerPoint. You don't really need them. What I want to make sure that you understand so far is that we did this at the beginning of the school year, but we didn't have the idea of the mole. So now we're taking the mole and molar mass and we're putting it to percent composition and what a compound is made of, the percentage-wise, how percentage of elements found in a compound. Sorry, I just completely messed that up. Now, what I am finding is that I cannot write on all of this side of the screen, so hopefully you can see what I have written here. I am going to be adding notes, so make sure you have room. I'll try to make sure to go through and check the camera periodically to make sure that you are seeing everything I'm seeing. So chemical formulas. Percent composition, you need to underline this, star this, or highlight this. This is percent by mass of each element in a compound. And this is the equation used to find percent composition. And what that basically means is that I can take the mass of the element, if I know the mass of the element, and the mass of the compound, times that by 100%, and that will tell me percent-wise how much of that particular element it makes up that compound. So I did a problem on the board for you. I asked you if I have 20 grams of a sample and it contains 16.0 grams of zinc and oxygen. We don't know how much oxygen yet, but I contain 16.0 grams of zinc so far. We could probably find the oxygen. I want you to tell me the percent composition of each element in that compound. And so the first thing I did here was I subtracted 16.07 from 20 grams. That gave me 3.93 grams of oxygen. So again, I didn't provide the oxygen amount to you, but based off of just subtraction, you can do this very easily. Nothing crazy or nothing hard. All of this right now should be a review. Now I want to know the percent of zinc and the percent of oxygen in this particular sample. So what I'm going to do is I'm going to take the total that I have of zinc, divide that by the compound, and multiply by 100 to give me 80.35% of zinc. I do the same thing for oxygen and I get 3.930 grams divided by 20 times 100 gives me 19.65 grams. So make sure you write this example in your notes if you're not already doing so. This is a really good brief reminder of what we've done in the past. Now, if you look here, the total percentages should always add up to 100%. That tells me that obviously that's a complete compound. So I wanted to make sure that you understood that. And let me see here. All right, so we can, if you look over here, the percent composition from a chemical formula, we can figure out the percent composition of a chemical formula. So the first thing we need to understand is what is a chemical formula. So let me erase this really quick. So a chemical formula is what's used to read the compound. So like CH4, C6H12O6, these are chemical formulas, and we can use the subscripts in these formulas to actually help calculate the percent composition. And so you're probably thinking, well, what does she even mean by that? So subscripts in the formula are used to calculate the mass of each element found in 1 mole of the compound. So the subscripts, remember CH4, this is a subscript. C also has a subscript, you just don't see it. It would actually be C1H4. So the subscripts in the formula are first used to calculate the mass of each element found in 1 mole of the compound. So I'm going to keep repeating that. Percent composition can also be used to determine the mass of a certain element that is contained in a sample. So I'm going to give you an equation that I want you to add here. So the percent by mass, so it's going to look similar to the top, but there's just a little bit of change to it, is the mass of the element in 1 mole over the molar mass of the compound. So make sure you're adding this in your notes, times 100. Times 100%. So percent by mass equals the mass of an element in 1 mole divided by the molar mass of the compound. And this is how we're going to find the percent composition from a chemical formula. So we're going to have to do some conversions. We're going to have to convert from grams to mole, and we're going to have to find the molar mass of the compound. So I'm going to give you an example of that. I want you to calculate the percent composition of Cl2O7, which is known as dichlorine heptaoxide. So calculate the percent composition of Cl2O7. So right now, when you're looking at this, what information do you have? Well, first of all, you have Cl2O7, and that tells you something. You can figure out the molar mass from there. So let's go ahead and do that first. So, well, actually, let's backtrack a little bit. Let's figure out the mass of just the chlorine in 1 mole of Cl2O7. So 1 mole of Cl2O7. So the chlorine, the amount of that would be Cl times, it would be 35 times 2. So the mass of chlorine in 1 mole of Cl2O7, right? All I did was took the 35, which is the molar mass of chlorine, and I multiplied it by 2 because I have 2. I did the same thing for oxygen. So the mass of oxygen in 1 mole of Cl2O7. So that would be approximately 16 times 7. And I did the math here. I got something along the lines of 70.90 grams and 112.00 grams. So far, I hope you're following, right? All I did was I found the molar mass of each individual element, and then I multiplied by the subscripts. Nothing crazy. Now, what I'm going to do is I'm going to find the molar mass of Cl2O7. And it should be something along the lines of 182.9 grams per mole. If you do the math, 70.9 plus 112 is approximately 182, and that looks good to me. Now what we're going to do is we're going to take each individual mass and divide that by the molar mass of the compound. So the percent of chlorine equals 70.9 divided by 182.9 times 100, and then the percent of oxygen equals 112.00 grams divided by 182.9 times 100. And then when I did all the math, I got 38.76% of chlorine, and I know I'm probably in the way, but it'll be fine. 61.24% of oxygen. So using the molecular formula or the chemical formula, I was able to infer how much percentage-wise I have. And I didn't even have to convert moles here. So we're not converting moles just yet, but we're getting there. I think this is just a little bit more of a thinker than the last one. So I didn't give you the exact grams, but you found the grams just based off of how much chlorine I have within the chemical formula. So what I want you to do is figure out, and I'm going to write that over here because you probably can't see. I'll erase this. So your job right now is to figure out the percent composition of MgF2. So that's your job. We'll see what you get. So you might want to pause. Try it out, check with your partner, see if they got that. All right, the next way we can figure out percent composition is the percent of water in a hydrate. Now, we're not gonna do math when it comes to this, but it's good to know. And the reason why this is good to know is because when we're dealing with ionic compounds, typically ionic compounds will have water associated with their crystal lattice. So an ionic compound, I'm gonna write some notes over here for this. An ionic compound naturally contains water, and we call this a hydrate. And you already have the definition for a hydrate. It means that it's a compound that has one or more molecules bound to each formula unit. So for every one formula unit you have some amount of water, and that's a hydrate. A good example of this is cobalt to chloride. And typically how you see this is you see the the name, and then right next to it you have like a multiple sign with the coefficient of H2O. And so basically what this is saying is that for every 1 formula unit of cobalt 2 chloride I have 6 molecules of water. That's all that's saying. And while I think that this is really good to know, I'm not going to put any math to this one, only because it's not used quite as often in chemistry. So I am not going to force that on you. All right, I got a slide, and I don't have anybody here to slide for me, so give me a second. All right, so empirical formulas. I did notice that I actually put a little bit, this point here, I want you to cross out. So I want you to cross that out because I don't know what I was thinking when I was writing this, and then I looked at it and I was like, oh crap. All right, so empirical formula. A formula shows the lowest whole number ratio of the elements in a compound. You should definitely know that for an empirical formula, because an empirical formula can be different than a molecular formula. And I'm going to show you how that is, and I'll compare the two here in a minute. Now, what I want you to add, instead of this point, I want you to put ionic compounds can only have empirical formulas. So like I said, I don't really know what I was thinking when I wrote this point, but ionic compounds can only have empirical formulas. However, molecular compounds, so molecules, can have empirical and molecular formulas. So I'm going to spend my time right now talking about the empirical formula. Like I said, I have a lot of notes to add, and in this slide is one of them. You're going to be using plenty of notes. So a good example, the subscripts in a formula represent the molar ratio of the elements in that compound. So when I say I have C2H4, it shows me that for every 2 carbon I have 4 hydrogen. But we can break that down even further. So an example of a molecular formula is C2H4. Now the molecular formula is C2H4. We know we need 2 carbon for 4 oxygen, or excuse me, 2 carbon for 4 hydrogen to make this particular molecule. But the empirical formula is a little bit different. The empirical formula, remember, is a formula that shows the lowest whole number ratio of the elements in a compound. So I could break down 2 and 4 even farther. And I could say, so again, this is the molecular formula, which I'm going to talk about again on the next slide. The empirical formula would be CH2. Same ratio. So for 2 to 4, the ratio can be broken down even further, 1 to 2. And that's what it means by that lowest whole number ratio of elements in a compound. That's the empirical formula. So like I said, the subscripts in a formula represent molar ratio of the elements in that compound. And so how we use this is in a process known as elemental analysis. So in elemental analysis, what is going on is that an unknown compound I know I'm in the way, can be broken down to determine percent of each element contained in the compound. Okay, so like I said, elemental analysis is the unknown compound, so any unknown compound we have can be broken down to determine the percent of each element contained in the compound using the empirical formula. It's a little different. It definitely takes some thinking to do. So I'm going to give you a series of steps on how you would do this. I'm not going to erase it elemental analysis, but I'll erase the top and then add the steps on how we do this. So how we go about this, the bell's not gonna ring yet, so. How we go about this is in a series of steps. So the first thing you're gonna do is you're always going to assume you have 100 grams of every sample. This is to ensure that you can convert percentages very easily to their gram form. All right, and I'll show you what I mean by this here in a second. The second step you're going to do is you're going to use molar mass to convert grams to moles. So all these things you can already do. Easy, I can assume 100 grams of something. The next thing, converting molar mass, or excuse me, using molar mass to convert grams to moles. I don't think that's too hard, we've just been practicing that. The third step is kind of weird. So you're gonna divide moles of each element by the smallest value you get. From step 2. So again, you're going to, over here, you're going to go from grams to moles. Whatever the smallest value is, you're going to divide the moles of each element by the smallest value you get in step 2. And then finally, the fourth step, each number is equal to the subscript of the corresponding element in the empirical formula. All right, so like I said, the first thing, assume you have 100 grams of every sample. Convert from grams to moles using the molar mass. Then you're gonna, from here, you're gonna look at the numbers, whichever one's the smallest, you're gonna divide that number of moles by that smallest value. From there, you're then going to equate the number of subscripts that you get after you divide it. And there is another step that if you still don't get a whole number that we are going to do, and I'm going to show you in my example. I'm going to leave this on the board for like another 1 minute so that I can, so that you can write, and I'll go ahead and delete elemental analysis. I'm going to do the example over on this side, so if you need to write, you might want to pause. All right, so what I want you to do is, I have a compound. I have a compound that contains iron and oxygen. So Fe and oxygen. O. And we know, there goes the bell, and we know that I have 69.94% of Fe. Okay, so of my compound, whatever that may be, 69.94% of it is Fe. The other 30.06% is oxygen. What I want you to do is find the empirical formula. Find the empirical formula of the compound. So how do we do this? The first thing, you are going to assume 100 grams of a sample. So that very easily converts the percentages to 69.4 grams of Fe, 30.06 grams of oxygen. Very easy. So now, if I assumed I have 100 grams of a sample, 69.94 grams of Fe, 30.06 grams of oxygen. Nothing crazy, you're just assuming things, and that's okay. So now what you're going to do is you're going to convert these grams to moles. So this would be over 1, and this one would be over 1. How do I convert grams to moles? Grams goes on the bottom. Moles goes at the top. For every 1 mole of iron I have 55.85 grams. Which would equate to 1.252 moles of Fe. Notice that this is not a whole number. So we have some tricks that'll help us get there. The next one, 30.06 grams of oxygen. So 1 mole of oxygen gives me 16.00 grams of oxygen, which equates to 1.879 moles of oxygen. So, like I said, all we did was convert from moles. Now I'm going to go ahead and erase these rules because you've already done that. You've already written that. And I'm going to bring this over here. So the first step I did, again, I assumed I had 100 grams of the sample. That easily converted the percentages. I then found those, I made those percentages grams, and I found the moles of each of those samples. So far, nothing crazy. So since you have decimals, you're going to divide by the smallest of the results. So which of these two is a smaller number? I'll give you a minute. Okay, you should have said 1.252 moles of Fe is smaller than 1.879. So now step 3, what you're going to do is you're going to take 1.252 moles of Fe divided by 1.252, no moles or anything. You're just going to divide the two, and you get 1 mole of Fe. Notice I don't have anything at the bottom, no units, so then that's why that moles of Fe did not cancel out. Now, when I take 1.879 moles of oxygen divided by 1.252, I get 1.501 moles of oxygen. Still not a whole number. Okay, so I can't use this as for my empirical formula. Because remember, we said the lowest whole number value. 1 is a whole number, 1.5 is not. And no, we cannot just round and say I have 1 to 2. We are going to use a different method. So now what we're going to do, since oxygen is not a whole number, you're going to multiply both, or multiply by 2 for both of these mole values. So I would just round this and I would get 2, and so 1 mole of Fe times 2 gives me 2 moles of Fe. And 1.5 moles of oxygen times 2 gives me, why can't I think? 3 moles of oxygen. So now I have, and for every 2 moles of Fe I have 3 moles of oxygen. So your empirical formula is Fe2O3. So it's a lot of work to get that empirical formula. And another point you should always know is that metals always goes first. Metals always come first. So like I said, a lot of work, but if you follow those steps, they'll always get you through. So what I want you to do is I want you to find the empirical formula. Let me erase all that. Well, I'll write it over here. Find the empirical formula when you have 63.65% of nitrogen and 36.35% of oxygen. This is what I want you to do. I'll erase the rest of this and slide. So it's weird stuff, but it's using all the knowledge we've had. I told you in the beginning of the school year this was going to come back to us, and everything is now coming back full circle. So hopefully you already wrote that down or you're practicing that. So the last, but certainly not least, we're going to look at molecular formulas and how that is different than empirical formulas. You probably already know how this is different, but let's go ahead. So molecular formula tells us how many atoms of each element are present in one molecule of a molecular compound, which maybe you're thinking, how is that different than an empirical formula? Remember, empirical formulas use the lowest whole number ratio. So if I have C6H12O6 and I have C2H4O2, these two examples would have the same empirical formula. They would both have CH2O. That would be the empirical formula for both of these. Two completely different compounds. One is glucose, one's acetic acid. This is what makes vinegar bitter. This is what tastes really good in cereal. So sugar versus vinegar, very much different, but they have the same stuff, but their empirical formula is the same. So there is some differences here. So I kind of already gave you the examples. Now you can have some molecular formulas that are also the empirical formulas. So CH4, that's the smallest whole number ratio you can go to. So this is both the empirical formula and the molecular formula. Not all of them can be that way. Like I said with that other example, I have H4O2 and C6H12O6. The empirical formula for both of those is CH2, but they both have a different molecular formula. So how can we go from empirical formula to molecular formula? Guess what? We got this. We got some steps here. Step 1, you're going to calculate the molar mass of empirical formula. I'm sorry I'm putting EF, but this is taking a long time. So calculate the molar mass of the empirical formula. Second step, divide the molar mass of compound by empirical mass formula. The empirical formula mass, excuse me. So what I calculated here, I am then going to divide the molar mass of the compound by that. So already you're looking and saying that I have to give you a lot of information here. The third and final step, you're going to multiply subscripts in the empirical formula by whole number found in step 2. So guess what we're going to do? So if I have an empirical formula of BH3, my empirical formula is BH3, and it has a molar mass of 27.2 grams per mole. What is the molecular formula of the composition, or of the compound, excuse me? So a lot of words. All I'm asking for is for you to use the empirical formula and the molecular mass of the compound to figure out what the molecular formula of the compound is. We cannot assume that just because the empirical formula is BH3, that the molecular formula will be BH3. So then what I'm going to do is I'm going to follow my steps. Calculate the molar mass of the empirical formula. So I have BH3. The molar mass of that would be 10.81 plus 1.01 times 3. And that should give you 13.84 grams per mole. Grams per mole. That's the empirical formula. I calculated the molar mass of that. Now it says divide the molar mass of the compound by empirical formula mass. So I've given you that empirical formula mass. Or excuse me, I've given you the molar mass of the compound. And I found the molar mass of the empirical formula. So I'm going to take 27.2, divide that by 13.84 to give me 2. The third step, multiply subscripts in the empirical formula by the whole number found in step 2. So I have my empirical formula here, BH3. I'm going to multiply that by 2. And I get B2H6. And that's how we find, from empirical formula, that's how we find the molecular formula. So what I want you to do is, this is the example I want you to do. If I have an empirical formula of CH with a molar mass of 78 grams per mole, what is the molecular formula? So I'll let you try that. I'm going to erase all this while you're working on that. If you have any questions, please email me. I do plan, like I said, I do plan on being here, but if I'm not, if things go weird and wacko, just please email me. I will take my computer with me. It'll be packed with me, so when I get the opportunity, I will check on you guys. I'm not trying to leave you high and dry. I'm really sorry that I have to not be at school. It's not ideal for me. So this is the last thing I'm leaving you with. Please reference this video when you're doing those questions, the review questions that you're going to do after this video. Also, tomorrow's homework, the percent composition worksheet, reference this video, reference the reading. It will really help you. You just need to be sure to look and know what you're looking for. What is the question asking you for? All right, with that being said, I'm done talking. I've talked too much. It's time to go home.